Okay, so we're going to continue on with our next section. Everyone's able to download it. I posted it, right? I think I did. Okay, good. So today we're going to be looking at assessment of risk and benefit in epidemiologic studies. So you guys remember risk from the biostat section? Yep, we're going to have a recap of it today, so that's good. Everyone's going to be crystal clear on that. So we're going to be looking at defining how we define study groups. We're going to be comparing risks within different study groups, so looking at absolute difference in risk, relative risk, and then review other measures of the impact of those risk factors, whether it be attributable risk in exposed patients, population attributable risk. We'll talk about how we can kind of calculate those. We're not going to do a ton of math on the test, or really kind of any math that I can think of, but at least know the concepts that are going into this and know how we're calculating these numbers. Then we're going to be looking at uses of different types of risk assessment data, so we can look at the application of this data to policy analysis. We can look at things like cost effectiveness analyses and things like that. And then we'll look at the application of risk measures to the counseling of patients. So when we're looking at causal research in epidemiology, it's going to require kind of two fundamental distinctions. So the distinction between people who do have and people who do not have exposure to our risk factor or protective factor, whatever happens to be we're looking at being studied. And so in this case, when we're deciding who's falling into this group based on either the risk factor or protective factor, that's going to be our independent variable, right? You guys remember independent variables? Right, it's what we are controlling, right? Then the distinction between people who do have and people who do not have a disease or other outcome being studied would be the dependent variable, right? So we're looking at these risk factors as they're independent. So I'm saying, okay, these people smoked, these people didn't smoke, and then the dependent variable is going to be, did they get lung cancer or not, right? And then these measurements are going to be subject to random errors and biases, as we've already kind of mentioned before. So researchers can be complicated by other requirements, right? So you may need to analyze several independent, possibly causal variables at the same time, including how they interact with one another. So we've kind of mentioned these already, but looking at the frequency of hypertension as being related to both age and gender. We see that you can have lots of interacting factors here. There may be some synergism. There may be some other ways that the other variable interactions that are occurring here. So for instance, before the age of 50, men are more likely to be hypertensive, but then after the age of 50, women tend to be more likely to be hypertensive, right? So looking at those changes and how those variables can interact with one another is an important thing we need to look at. And so you may need to measure different degrees of strength of the exposure to the risk factor, the duration of exposure to the risk factor, or both, right? So whether or not someone has been exposed to it for a long time or a short time, or maybe that kind of that dose-response relationship that we mentioned here. So measuring exposure to something like cigarettes would be in terms of how many packs per year the patient was smoking, which is going to be the average number of packs smoked per day times the number of years that person's been smoking, right? So that would be one way to measure the degree of exposure someone's had to a given risk. So, and then depending on that risk factor, it could be difficult to determine the time of onset of exposure, right? So getting those temporal relationships can be difficult in a lot of cases. So this can be true for risk factors such as sedentary lifestyle and excess intake of dietary sodium. So again, when do you determine that onset of exposure? So like a sedentary lifestyle, right? I could probably say from the womb. May not be for everyone though, right? It could be something that developed later on in life. For me, it became even more so after having a child. I just don't want to move anymore. But again, time to onset can be very difficult to determine. And so another complication of the analysis is the need to measure different levels of disease severity. So again, sometimes it could be easy. You could look at an exposure to being either present or absent, but in a lot of cases, you want to look at the severity of disease, and that can be much more difficult to determine unless you have a good, already kind of validated scale or whatever you're looking at to determine that. So despite the complexities, a lot of research still relies on the dichotomies of exposed, unexposed, disease versus non-disease. And so this is where you can find a lot of these things can be being popped up into these contingency tables. Very frequently, these 2x2 being the most simple varieties. I'm sure you guys remember seeing these. But essentially, when we're looking at these patients here, we can divide them up as to either having the risk factor either being positive or negative, and then looking at the disease stats either being present or absent. You guys remember what type of statistical test this looked like? Some type of square? Like a chi-square, right? So again, you're looking at observed versus expected frequencies. A lot of similar information can be drawn from this, but very frequently in these epidemiologic studies, you can look to see, okay, is the risk factor there? And then if it is, who had the disease actually present, right? And so then you can notice your total columns are pretty easy how you're calculating those, right? So we can do a lot of information with this. We can look at things like looking at risk ratios, odds ratios based on the information we have here. So we're going to come back to this table and just remember that these variables are going to stay consistent throughout the lecture, where A is going to be people who have the risk factor and are positive for the disease. B will be people who have the risk factor that are negative for disease, and similarly for C and D for people who do not have the risk factor. So causal research is going to depend on the measurements of these differences between the groups. And so with something like a cohort study, we know that the difference is going to be between the frequency of disease in persons exposed to a risk factor and the frequency of disease in persons not exposed to the same risk factor, right? So that's our independent variables. We're deciding who has the risk factor versus who doesn't, and then we're measuring the disease outcome. Versus in the case control study, the difference here is that the frequency of risk factors are going to be in case subjects who've had the disease versus those the controls who had not had the disease. There you're looking for the presence of the risk factors between those two groups. Exposure could be to lots of different things. We can look at nutritional factors. So it could be high saturated diet, high fructose corn syrup, whatever happens to be. Environmental factors. So for instance, if you had radiation levels being measured after the Chernobyl disaster, certainly behavioral factors are a big one. Sedentary lifestyle, exercise, all the different things. Physiologic characteristics, medical interventions, or even public health interventions. So vaccines being a pretty easy one to point to. So how do we compare risk in these different study groups? Hopefully you guys can teach me this, right? Because you guys already know how to do risk. Awesome. Okay. Well, for anyone that maybe forgotten, we'll go over it. So the differences in risk are going to be measured in either absolute terms or going to be in relative terms. So when we say absolute terms, what does that mean? It's going to be the absolute change in risk that happens between the different groups. So again, that's oftentimes you're going to be subtracting risk from one another, right? So very simple, just subtraction. So we're going to get absolute risk reductions. We're going to get attributable risk rates, things like that. They're going to be done by just adding or subtracting the risks from one group to another. On the other hand, if we're looking at relative risks or relative terms of risk, how are we computing that? Yeah, we're doing ratios of it. We're dividing one risk by another. And so it's important to remember between the difference in how you get the absolute versus the relative risk in those situations. So the method is going to depend on the type of study that's being performed, right? Because we know that different types of calculations are going to be more appropriate for different types of studies. So case control studies are going to allow for investigators to obtain only a relative measure of risk. And why do you think that is? So it's really going to be because when we said case control studies, are those retrospective or prospective? Right, we already said those are mainly retrospective, right? So we're already looking at the number of people who have had the outcome that we're looking for, right? And then we're matching them with the number of people who have not had the outcome. So it's all retrospectively being done. We're already seeing the outcomes that have occurred. And so what we can do is look for the relative risk of the the risk factors they may have had. But because you're not looking at new incidents of disease, and you don't have a whole population that may be at risk or a whole sample that may be at risk, that's why you're looking at relative terms. You can't do absolute numbers because with prospective studies, like a cohort study, you can look at a whole group of people, your sample, and say that these are all the people who are at risk, and where is the new incidence of disease as you go forward. Because with case control studies, you're starting out with people who've already had the outcome and then matching them to a group of people. You can't really do that same kind of math. So, or at least have the same type of, because you don't know who's really at risk for having that outcome at that point, because you're only looking at cases and controls. So essentially, you need to look at relative terms when you're doing case control studies, whereas if you did a prospective cohort study or randomized controlled trial, this is going to allow you to do both absolute and relative measures of risk. So this is why if I do a prospective randomized control trial, I can do absolute risk reduction. I can look at risk ratios and things like that, versus with retrospective studies like a case control, really odds ratios are the big thing I'm going to be looking at there. I cannot do an absolute odds reduction or something like that because it doesn't really exist. Everyone with me so far? Okay, and just realize this is going to provide different information for our purposes. So after the differences in risk are calculated by the methods, the level of statistical significance has to be determined to ensure that any observed difference is probably real, right? So this is signified by our p-value, right? And we're usually looking for p less than 0.05, absolutely. So again, we're saying that it's very unlikely that the difference we're seeing is due to chance alone. So when the difference is statistically significant but not clinically important, the difference could be truly real, but it's going to be trivial. It really doesn't matter much for our purposes. However, when the difference appears to be clinically important but is not statistically significant, it may be a false negative, which could be a beta error, otherwise known as what type of error? A type 2 type of error, right? Because we're saying that there could be a real difference there, but we didn't detect it, so it's a beta or a type 2 error. And it could be an issue with the sample size being small, or it just could be a chance finding. It could be that there really is no difference between the groups as we're with what we're measuring. So looking at absolute differences in risk, disease frequency is usually going to be measured as the risk in cohort studies and clinical trials. And then frequently rate will be used when disease and death data are coming from population-based reporting systems. You guys remember what the difference is between risk and rate? So how do you calculate risk? So you would take the number of outcomes that you have divided by the total number of people in your sample size, right? So if I had, say, 100 people that I was following and 10 of them had a heart attack, what would be the risk of having a heart attack in that group? 10%, absolutely. So and on the other hand, though, if I'm looking at a rate, how would I calculate that? Because remember we talked about it? Because remember, rate is better for showing kind of that force of mortality. So say, for instance, if you had a whole bunch of people die at the beginning, that changes your velocity of mortality versus if you had a whole bunch of people die at the end. The difference there being your denominator changes over time, and with rate, you're using that midpoint population, right? So if I follow those 100 people for a year, my midpoint population would be 6 months in, and that's the denominator I'm going to use to determine that, right? So they can be very similar to risk, but the number is probably going to be different to at least a small degree. So anywho, but that's going to be better for a big population type of data that we're looking at. So absolute differences in risk or rates can be expressed as a risk difference or as a rate difference, right? So we're just subtracting one from the other to figure out what the actual difference is here. So in the case of a risk difference, this is going to be the risk in the exposed group minus the risk in the unexposed group, okay? So I had two groups going forward. I was seeing who had heart attacks, 10% in one group, 5% in the other. What would be the risk difference? 5%, right? Because it's just 10 minus 5. 5, easy. Looking at rate, it's going to be calculated the same way, except you're going to subtract the rate in the exposed group minus the rate in the unexposed group. Okay, so similar concept. It's just a matter of figuring out what your denominator is going to be between a rate and a risk. Everyone with me so far? Okay. So when the level of risk in the exposed group is going to be the same as the level of risk in the unexposed group, what's your difference going to be? 0, right? Because if 10% died in one group, 10% died in the unexposed group, it's going to be 10 minus 10, thus you get 0, right? So the conclusion here is that the exposure makes no difference to the disease risk being studied. So it doesn't matter whatever risk factor I was looking at had no effect on the actual incidence of the disease the outcome actually occurring. And so if an exposure is harmful, such as cigarette smoking, the risk difference is expected to be greater than 0, right? Because if I was looking at patients who smoked versus those that did not smoke and looking at death, I would expect the risk in the smoker group to be higher, right? And lower in your non-exposed group. And so you subtract one from the other, should be greater than 0, right? Mm-hmm. On the other hand, an exposure is protective, something like a vaccine, the risk difference would be expected to be less than 0. Or a negative number would equal a reduction in the disease risk in the group exposed to the vaccine. So just keep in mind, if you see either things that are less than 0 or greater than 0, that's going to be changes in either the risk of something occurring or is it going to be more protective. So keep in mind, if you're looking at a number, what that really is going to mean. So the risk difference is also going to be known as the attributable risk. That's an estimate of the amount of risk that is attributable to that particular risk factor. Okay, so just know risk difference, attributable risk, all the same thing. We'll show you some graphs in a little bit to kind of show some of the differences between these. So in the previous slide, or previous table, the risk of disease in the exposed group ended up equaling A divided by A plus B. And so we remember that A being the group of people who had the risk factor and developed the disease, plus the group of people, B being people who had the risk factor and did not develop the disease. So that's your total group, right? And so risk is always going to be your total at-risk population, right? odds you're going to see it's a little bit different, but for risk, it's always going to be your total at-risk population. So it'll be A divided by A plus B, and this will give you a risk in the exposed group. Similarly, you're going to do the same calculation for the unexposed group, and so when you were to actually put these down into to calculate it, you can see here it's just one minus the other. So again, don't get scared by the variables, just know what they're representing. So again, the difference in risk here is also going to be the attributable risk. Okay, just for reference back to this table, again, we're just looking at A, because these are the people that were exposed to the risk factor and had the disease divided by the total here. Because you're looking at the total group of people that are at risk. All right. So the next figure is going to provide some data on age-adjusted death rates for lung cancer among adult men smokers and non-smokers, both in the U.S. and the UK, in 1986. Okay, so when I say age-adjusted, what does that mean? You're taking age out of the equation, so to speak, for how that's impacting. Because again, we know that older patients are more or less likely to die. More likely to die, unfortunately. It's just the inexorable march of time. Younger patients are more likely to live. So by taking the age out of the equation here, you can make sure you're kind of comparing apples to apples and looking specifically at the differences between smokers and non-smokers. And again, even more restrictive because we're only looking at men in this situation. So for the U.S. in 1986, they were to find that lung cancer death rate in smokers was 191 per 100,000 population per year. So if you followed 100,000 people, 100,000 men for that whole year, 191 of them would die, right? If I followed 200,000 people for that whole year, you'd have double that. So the rate in non-smokers happened to be 8.7 per 100,000 per year. Why do I do the 100,000? Why don't I just do like 100 people?
You're going to catch enough.
Well, I could express it like that, but then someone said, does anyone say decimal? It would just be a decimal at that point, right? So I'd be looking at 0.00 or whatever, 87 people per 100. And that doesn't really make sense to the layperson when they hear that. So by expanding out the population that you're looking at by saying 100,000 versus, say, 100, that number makes more sense. So again, 8.7 makes a lot more sense than 0.0087 people per whatever. So again, because the death rates for lung cancer in the population were low, less than 1% per year, in the year for which the data are shown, the rate and the risk for the lung cancer data would be essentially the same. So remember, that makes sense because if our actual incidence of the outcome is very, very low, your midpoint population doesn't change very much. And so your midpoint population and your starting population should be relatively similar, and that's why the actual risk and the rate don't differ very much from one another. Okay, go back to that lecture if you need a refresher on that. So looking at the risk difference between these two groups, it's pretty easy to calculate. You just do the following. So you'd say, okay, 191 per 100,000 people per year minus 8.7 per 100,000 people per year, and you end up getting an absolute risk difference, or the attributable risk due to smoking, being 182.3 people per 100,000 per year. Does that make sense? This is one minus the other, and that's the attributable risk. This is saying that this is the risk of people dying due to specifically cigarette smoking alone, right, in these men. Because if these guys had not been smoking, you'd end up having just 8.7 of them would have died on average, right, based on what the information they're saying is. So if you were to look at, say, the attributable risk in the UK, you can see here that fewer people were dying due to cigarette smoke here, 166 versus 7, and then you can see the attributable risk here. So it's a little bit lower in the UK than in the US for this given year, but this is what the absolute risk difference would be. So again, you're just looking at the total number of people here that have died, smokers here versus the non-smokers, and you can get this risk difference just by subtracting one from the other. So the relative risk, and so when we say relative risk, what do you think we're going to be doing with those two different risk numbers? Yeah, now we're going to start dividing them by one another. So the relative risk is going to be that relative measure. It's going to be also known as the risk ratio. So you can oftentimes see it being abbreviated as RR. It's going to be that ratio of the risk in the exposed group to the risk in the unexposed group. So if the risks in both groups are the same, what would your relative risk be? Should be 1, because the same number of people are having the outcome in both groups. So 10 divided by 10 is still 1, right? So relative risk of 1 means there's no difference between the groups. Again, remember, this is very similar to what we were looking at with confidence intervals and your point of significance. So when you're dividing one by the other, 1 is going to be kind of your critical number here. If the risk of the two groups are not the same, then if you calculate a relative risk, it's going to provide a way of showing in relative terms how much different, greater, or smaller that risk in the exposed group is going to be compared to the unexposed group. If the risk for disease in the exposed group is greater if an exposure is harmful, or it's going to be smaller if the effect is going to be more protective. So if you imagine cigarette smoking, you're looking at people who smoke versus don't smoke, what do you think the relative risk is going to be? Greater than 1 or less than 1 for, say, death? Should be greater than 1, right? Because we know this is going to be a harmful effect. This is a risk factor for death. So in the case of it, say looking at the contraction of measles in patients who are vaccinated versus weren't vaccinated, what do you think the relative risk would be for those who are vaccinated to contract measles? Should be less than 1, right? Because if your risk is going to be smaller in the group that were vaccinated versus those that weren't not. So here again, the math is going to be the same. You're still calculating your risk in the same way because you're still getting your risk in the exposed group is still being calculated as the number of people who had the outcome divided by your total population and those that had the risk divided by the people who are unexposed. Okay, so risk of exposed divided by risk of unexposed. That's how you get your risk ratio. So again, you can reference back to this table. So the data on lung cancer death rates were used to determine the attributable risk in the previous figure. So again, the same data can be used to calculate the relative risk. So if we were looking for men in the US, we saw that 191 per 100,000 divided by 8.7 per 100,000 gives us a relative risk of 22. So what do you think that means?
22 times greater risk of dying of lung cancer if you are a male smoker.
Right, so the risk as compared to those who do not smoke is 22 times higher. That's what that number is trying to tell you, right? So you have 22 times the risk when you're smoking versus those that did not smoke. Similarly, you could do the same thing for those in the UK group. If you did 166 per 100,000 divided by 7 per 100,000, you end up getting a relative risk of 23.7, indicating that smokers are almost 24 times as likely to die of lung cancer as were non-smokers, right? So again, not clinically probably all that significant between the two. We can see here that the risks are going to be relatively similar between the two populations here. So again, in relative risk terms, the value of the risk for lung cancer death in the unexposed group is always going to be 1. So again, that's why 1 is always your baseline, your control group, your unexposed group, that's always going to be 1 because their risk is your baseline. Okay. So the conversion from absolute to relative risk is shown in the next figure, so we'll show you that. And absolute risk is going to be shown on the left axis, and you'll look at relative risk is going to be shown on the right axis. We'll kind of see graphically how you can compare these. And it's important to consider the number of people for whom that relative risk is going to be applying to. So a large relative risk that applies to a small number of people may produce few excess deaths or cases of disease, right? So if my people who have been exposed are very small, then I may not expect to see a whole lot of extra deaths from that. But a small relative risk that applies to a large number of people may produce many excess deaths or cases of disease. Okay, so what that means is this is really important when you're looking at things like cost-benefit analysis for, say, an intervention that prevents death from some disease. Right? If it's a relatively small number of people who are being impacted, even if exposure to something is causing a huge huge increase in the relative risk, if it only affects a small number of people, then it may not get as much bang for your buck as if you're affecting something that has a relatively smaller increase in risk, but is affecting a large number of people, right? Because again, it's all going to be relative to your sample size you're looking at, your populations. So here you can see the absolute risk difference. Here you're going to be looking at the absolute risk difference between these guys here, and you can notice that when you're subtracting the smokers from the non-smokers, this is your attributable risk, or your risk difference. But then when I'm dividing one versus the other, this is where I'm getting the relative risk. And here, the American patients, it was 22 times the risk in this case. So again, this is just 22 times higher than this risk for the non-smokers. That kind of makes sense from a graphical standpoint. So this column is 22 times higher than this column, and then also the difference here is going to be what we saw in the previous slide. Okay, so again, based on the symbols previously used, we can see that the risk of disease in the exposed group, as we mentioned, is going to be A over A plus B. So again, it's going to be the people who had the risk factor, who had the exposure, who developed the disease, divided by that whole sample. On the other hand, though, if we're looking at odds, the odds are going to be the disease in the exposed group is simply just going to be A divided by B. So it's the odds of someone getting the disease divided by the odds of someone not getting the disease, essentially. So if A is small compared with B, you're going to see the odds would be very similar to the risk. But in a lot of cases, if that's not the case, you're going to see the odds can be very, very different from the risk you ended up calculating. And so again, odds ratios are going to be really important when we're talking about especially retrospective or case control studies. So in a particular disease that occurs in one person among a group of 100 persons in a given year, right? I could say that the risk in this case was going to be 1 in 100, or 0.01. Makes sense. Now, but the odds of that disease in that case would be 1 to 99, or 0.0101. So you can see it's a little bit different when you have a very small incidence occurring in this group, but if it was something like lung cancer rates, you're going to see that the odds are going to start to climb up pretty quickly. So everyone get the difference between how to calculate risk versus how to calculate odds. So it's an important distinction to make here because it will give you very different numbers in a lot of cases. So if the risk of the disease is relatively large, say greater than 5%, then the odds ratio is not going to be a good estimate for the risk ratio, right? So never mix up trying to get a risk ratio from odds. The odds ratio can be calculated by dividing the odds of exposure in the disease group by the odds of exposure in the non-disease group. Or so in this case, the formula is just going to be, when you're doing an odds ratio, it's just going to be the odds of A divided by C over B divided by D. Otherwise, you can just kind of simplify it to A times D over B plus C. Just know that basically you're just taking the odds of those that are exposed and having the disease versus those that are not exposed having the disease and dividing one by the other. Okay. So again, moving back to here when we were looking at the odds ratios, basically saying, okay, who has the disease, who's positive for the risk factor versus those that weren't. So A divided by C. Here's going to be B divided by D. And then you can see how by dividing one by the other, you can see how the variables kind of reciprocate there, and you get that A times D divided by B times C. Okay, so the fact that the odds ratio is the same whether it's developed from, say, a horizontal analysis of the table or from a vertical analysis is valuable for when we're analyzing some of this data from case control studies. So even though a risk or a risk ratio cannot be calculated from a case control study, odds ratios can definitely be calculated. We've mentioned this already. And so odds ratios from a carefully performed case control study is going to be a good estimate of what that risk ratio might have been had you performed a much more costly and time-consuming prospective study. It can be close. It depends on the type of study you're doing, but in some cases that's going to be your best approximation, especially when you're doing things where you cannot do a randomized controlled trial due to ethical issues. By looking at case control studies and getting those odds ratios, you can at least get as close as you can. And so, like we said, the odds ratio may be used as an estimate of the risk ratio if the risk of disease in the population is very low, especially if the risk ratio is less than 1%, and probably if it's less than 5%. But the lower that incidence is, the more likely your odds ratio is very similar to your risk ratio. So if the risk for disease is the same in the group exposed to a risk or protective factor, we mentioned this, that the risks are the same and you're trying to get the relative risk, it's going to be 1, because 10 divided by 10 is always going to be 1. And so hypothetically, you could have a risk ratio that would be 0, meaning that the individuals who are exposed to, say, a protective factor had no risk for the disease whatsoever. So again, if you had 0 divided by 10, it'd just end up being 0 at that point. It's very unlikely you'd have that happen unless you were working with a very small sample size where the incidence is so rare that you did not pick up on that. Or it could be infinity. Say the individuals who are exposed to a risk factor have some risk, and the unexposed individuals have no risk whatsoever. So again, your denominator at that point would be 0, and then you don't really get a whole lot of useful information from that point. So when dealing with risk factors, the exposed group is the numerator because the number is going to get larger as the risk factor has a greater impact. Kind of make that sense of that. And then that risk ratio can also be expressed with the exposed group in the denominator, but it's not super common in the medical literature. So really just keep it to where the exposed group is going to be in the numerator. That's how it's done most frequently. Okay. So let's see if we're looking at, say, cigarette smoking and myocardial infarction. The risk of this disease for smokers is going to be greater than that for non-smokers. I think we can probably make that assumption. And then it's acceptable to put smokers in the numerator and express the risk ratio as 2 to 1. So again, the risk ratio of 2 basically. The risk of myocardial infarction would be about twice as high for smokers as for non-smokers. Otherwise, if they had the same sex, age, and health status. If you can kind of control for all those other things you see here, the MI is going to be about twice as high for smokers versus non-smokers. So it'd also be acceptable to put the smokers as the denominator, express the risk ratio as half. So say 1 divided by 2, or say 0.5, and saying that non-smokers have half the risk of smokers. So if you flip the numerator and denominator, just remember what that means for kind of what population you're speaking about, whether they're exposed or the unexposed. So again, be explicit in the nature of your comparison to make sure you don't get things flip-flopped and make it look like people who don't smoke have more MIs, because we know that's not the case. Another risk factor might produce, say, 4 times the risk of disease, in which case, the ratio could be expressed as either 4 or, say, a quarter, depending on how the risks are being compared. So just make sure to keep those straight. And then when the risk ratio is being plotted on a logarithmic scale, we'll show you that in the next figure, the distance to the risk ratio of 1 should be the same regardless of how the ratio is being expressed. I'll show you what that looks like in just a minute to make a little bit better sense of that. So mathematically, it doesn't matter whether the risk is going to be for the exposed group or for the unexposed group is in the numerator, but just universally, you're going to see in the literature that the risk of the exposed group is expressed in the numerator. This is really the most frequent way to see it being expressed. So although the equation for calculating odds ratio is differing from risk ratio, we know that when the odds ratio is calculated, same principle is going to be applying, in which case where we're keeping the numerator and denominator should be explicitly put there. But again, the math is going to be the same regardless. So if you have 2 risks, or say 2 rates that are being compared, if there's no difference, again, that rate difference should be expressed as 0. But when the same 2 rates are being compared by relative risk, or odds ratios, the condition of no difference is going to be represented by 1. So just remember that if you're subtracting one from the other, 0 is your point of no difference. And if you're comparing them by doing proportion, 1 is going to be your point of no difference. So you kind of see here that if you use a logarithmic scale, you can keep the distances here kind of the same, depending on how you're going to be expressing the risk here. So whether it be kind of in a 4/1 increase in risk, or whether it be 1/4. By using that scale, it kind of keep things pretty consistent there as far as the differences in length. Okay, so some other measures that we can look at for the impact of risk factors. So you kind of talked about risks and odds, and we're going to talk about those in other contexts now and how they're looking at these. So one of the most useful applications for epidemiology is to estimate how much disease burden is being caused by a certain modifiable risk factor, right? So this is something we can change. Most often it's going to be a behavioral change we can look at. And so this is useful for policy development because of the impact of risk factors or interventions to reduce those risk factors. Can be compared with the cost and cost-benefit analysis to see, like, okay, how much bang for our buck can we get by reducing or changing this modifiable risk factor. So in addition, health education is often going to be more effective when educators can show how big of an impact a given risk factor has on an individual's risk. So if you have numbers you can show people, it's oftentimes going to be more convincing than just to say, hey, you should recycle. Like, well, how much difference can I make by recycling, or whatever happens to be. So in addition to the risk difference, relative risk and odds ratios, the most common ways we're going to do this include the attributable risk percent in the exposed. We'll look at the population attributable risk, and then the population attributable risk percent. So these are all going to be basically the same calculations we've already done for risk and odds, just being applied to a little bit different samples and populations. So this is a table you can refer back to. We're done talking about this. We're going to talk about these in more explicit detail as we go forward. So we've already talked about these guys. These are going to be the ones we're going to talk about more in detail as we move forward. Again, I'm not going to ask you to calculate this on a test, but at least be able to understand the concepts that are going into it. Okay? These look scary. They're not that scary. Okay, so when we're looking at the attributable risk percent in the exposed, the answer, we're trying to answer a question. So say, among smokers, what percentage of the total risk for fatal lung cancer is due to smoking? So how do we answer that question? Here, it would be necessary to calculate the attributable risk percent in the exposed group, which is going to be abbreviated. This is AR percentage, exposed, so sub-exposed there. We're going to see there's 2 different ways we can do that. So we can either do it through an absolute difference in risk, or we can look at the relative difference in risk. Okay, so again, the calculations are going to be the same here. It's just looking at what our numerator and denominator are going to be. So looking at the following equations is going to be based on absolute differences. So here we can see that to get the attributable risk in patients who are exposed, so say the people who are smokers in the population, what is the attributable risk this has on lung cancer death? And so here what we can do is look at the risk of patients who are exposed minus the risk of those that are unexposed, divided by the total risk of those who are being exposed here. You multiply that at 100, so that way you can get your percentage here. Okay, so for instance, just to give you a concrete example, if we wanted to do this with that 1986 data for those male smokers, here what we could do is that we know for that population, we know that the risk in smokers was 191 per 100,000, right? And then it was 8.7 for those in the non-exposed, non-smoker group, okay? So we were able to divide that out by the number of the risk in those that are exposed, times it by 100. And so essentially what you end up getting is that you get this percentage of 95.4%. So does anyone want to take a stab at what that percentage means? Basically what it means is that the amount of risk of lung cancer death that is related to smoking in the whole population is about 95.4%. Okay, so I mean this is a pretty big risk factor for developing lung cancer death is due to smoking. A large percentage of it is going to be due to that. Okay. So similar, if you had, say, you did not know the absolute risk, let's say you didn't have that data beforehand, what you can do is take the relative risk, can be used instead to calculate that AR exposed. So you can do the following instead. So say I had a sample, I can get the relative risk here, divide it by, or subtract 1, and then divide it by your relative risk. The reason why we can use 1 here is because we know that the relative risk in the baseline group is always going to be 1, right? Because they're my baseline. So again, when I'm looking at relative risk, which is dividing one risk by the other, we know that that's always going to be 1. That's your baseline. So having a relative risk minus 1 divided by the relative risk can give you a similar number. So here, if we were to calculate that out, we saw that the relative risk was 22 in the smokers group, right? And then 1 is going to be in that non-exposed group, the non-smoking group. So you can divide that out and end up getting 95.5%. Okay. So even if you didn't know the absolute risk in each of those exposed and non-exposed groups, you can use relative risk as a means of calculating the same AR percentage exposed. Okay, so again, this is telling us that the percentage of lung cancer deaths related to smoking in the whole population is about 95.5% of those. Okay. So the percentage based on the formula is using relative risk is the same as the percentage based on the formula using absolute risk. But again, it works because we're using our relative risk in the unexposed group as 1 because that's our baseline. So just subtracting 1 by the other, divided by that relative risk for the exposed group, and you get the same values. Really, the only difference you might see is some rounding errors. So that's why the number's a little bit different, but essentially they're the same. Okay. The next thing we can look at is going to be this population attributable risk. And so we can say here that among the general population, how much of the total risk for a fatal disease is due to an exposure to Y. So say if we're going to be looking at lung cancer deaths. So again, amongst the general population, how many of the lung cancer deaths rather were due to smoking? So we can answer that question by looking at the population attributable risk. And essentially what we're going to see is the risk for the total population subtracted by the risk for the unexposed patients. Because again, if you take the risk for lung cancer death out of the whole population and subtracted by those that were not smoking, who's left? Right, the risk for people who were smoking, right? So that's basically all we're doing there to get that what is attributable to those who are smoking amongst the whole population. So this is not as useful to know for, say, counseling patients, but is considerable use for making policies, right? Because we want to say, out of this whole population, what is, the number of people who are dying from motor vehicle accidents, what is it, what percentage of those are due to drunk driving, right? So maybe we can, initiate a new drunk driving campaign in order to help limit that or to help to reduce that. So this is really important for policy's sake. And so looking at, say, the 1986 smoking data again, if we were to subtract the risk of the adult male non-smokers, so again we saw that was 8.7 per 100,000, from the risk of the total adult male population, so if they were to look at that information, you end up getting 72.5 for the whole year, then you'd find that population attributable risk to being 63.8 per 100,000. So that means that amongst the whole population, per 100,000 people, 63.8 of them were dying due to exposure to smoking, right? Or lung cancer deaths due to smoking. So this can be presumed that if there had never been any smokers in the U.S., the total U.S. lung cancer death rate in men would have been much lower. So it probably would have been a lot closer to 8.7 per 100,000 per year. Obviously, this is going to be not exact because there's lots of other causes for lung cancer and things like that, but this is going to be as close as we can kind of get with the information that we have. So then the excess here over this figure is going to be attributable just to smoking by itself. That makes sense for everyone so far? Hopefully? Okay. You can do some practice ones and it makes more sense. So population attributable risk percentage, so this is a little bit different than what we were looking before. So again, this is just looking at the total population attributable risk. Now we're looking at the percentage of this. This one's going to answer and say that among the general population, what percentage of the total risk of X, so again, fatal lung cancer, is due to exposure to Y, in this case, smoking. So as with the attributable risk percentage in any exposed, the population attributable risk is going to be calculated using either absolute or relative terms. And here you're going to see it's going to be calculated very similarly. So again, looking at the total risk minus your risk of the unexposed divided by your risk total. Notice that's calculated here, just changing what your variables are in order to get that number. And similarly, if we were looking at that same data, again, you can just add in your variables here. End up getting that in the whole population who had the risk or who developed fatal lung cancer, we saw that 88% of them were due to exposure to lung cancer, right? Or due to exposure to cigarette smoking, right? So 88% of those in the population that died from fatal lung cancer had exposure to cigarette smoke. That's basically what this is kind of telling you there. So you can do the same thing with, like, you know, the number of people who died from car wrecks. These are the ones that were, say, intoxicated. Similarly.
So it's just the percentage. Well, it's the population attributable risk, the expressed as a percent, is what you're saying?
Exactly. Yep. So instead of just looking at attributable risk, we got the attributable risk percentage. Similarly, you're doing the same thing here. So the PAR percent instead could also be calculated using the risk ratio, and again, this is going to be done very similar. You could use odds ratio if the information is coming from like a case control study, but it's necessary to incorporate one other measure into the formula, and so this is going to be the proportion exposed, or the PE. So this is one more variable you'd have to put in here, and so essentially this is abbreviated as PE, defined as the effective proportion of the population exposed to the risk factor. So in this case, the equation is going to be as follows. Notice here it gets a little bit more complicated when using relative risk. But essentially, the reason why we're using this PE is because this is going to kind of give us an idea of the number of people who are exposed within that population, or the proportion of them. So here in this example, for instance, in 1986, we could say that the PE is assumed to be 35% or 0.35 at that time frame. So we can just plug that information in here and subtract all that out and divide, and you'd be able to get the PAR percentage. We'll see it's going to be very similar to how we calculated it with the more attributable or the more absolute terms. Obviously, we know that this number changes over time, and so you could also do comparisons to say, okay, well, here's what it was in 1986 when the population the PE was 0.35. Now it is, say, 0.25. Now you can make it more comparable. You can see how things are changing over time to see how that exposure is affecting the death rates for, say, lung cancer or whatever happens to be. So in this case, if we were going to go ahead and use our relative risk in those who were smoking to have fatal lung cancer as being 22. Right, so he says 22 times the risk here, and you can use that PE of 0.35, plug that in, and you're getting a percentage of 88%. So you saw it's very similar to what we did with the other means here. Again, you don't have to calculate these out; just realize what's going into these equations.
How do you get the PE?
So that oftentimes is done through a lot of those registries that are being done. So again, if you were looking at, say, the census, or if you're looking at other types of large epidemiologic studies where they're looking at cross-sectional studies to say who's smoking in, say, this population. So you could do a study saying that on average this many people in Florida are smoking, or whatever it happens to be. So
How do you know how accurate they are?
that's a good question. How do you know how accurate it is? You have to go back and look at your source of information. Very similar to how I said, like, poison center data is always going to be fraught with underreporting, because again, if a doctor doesn't call us about a case, we never know about it, right? So because of that, underreporting is always going to be an issue. So that number, say, 0.35 could have been low for that time frame if they weren't accurately capturing that information. A very good point. A lot of things we are using is going to be fuzzy math at best. May not be the actual true numbers, but it could be even higher, it could be a little bit lower. It depends on how they measured it. Good point. So the next figure is going to show diagrammatically how the formula for PAR percentage is working. So Essentially what you're looking at here is that your absolute risk is going to be on the left side of the screen. I'll go ahead and use that laser pointer. All right, so we're looking at the attributable risk here in the population, and then we're looking at the relative risk here on the right side. So our population, so we can see the proportion of people who are exposed versus those who were not exposed, right? So again, 35% we're estimating as being the proportion exposed for those who are smoking, okay? So the absolute risk, is going to be for the people who were not smoking to be 8.7 per 100,000, and we know that those that were exposed or smoking were 191 over that. So that's how you're getting the absolute risk difference. And then here with the relative risk, again, you're just dividing those by one by the other. So that's where we're getting 22 here. And so again, this is all just relating the proportion of patients who are being exposed or not exposed and relating it back to that information we have about the attributable risk and also on the relative risk there. So kind of going back to what we said, so again, 35% of the population was representing the proportion exposed, or the PE, to the risk factor. So again, those are the people that were smoking. The remaining 65% of the population who were non-smokers, presumably. And then the right side of the y-axis was showing that relative risk for lung cancer death. And so again, for reference, the left side was still looking at the absolute risk for lung cancer death in that case. So the dark gray shading, light gray shading, and the light blue are going to be used to show that relationship between the risk factor smoking and the disease outcome, that lung cancer death, in the smokers and the non-smokers. So in that graph, you saw that the light blue represents the outcomes that are not attributable to the risk factor for non-smokers. And you saw the dark gray part representing the outcomes that are attributable to the risk factor for smokers. Right, so we saw about 8.7 per 100,000 were due just to the non-smokers. That would have happened anyway, versus the much larger, darker gray portion of the graph were going to be for the attributable risk due to smoking itself. And then the light gray bars representing the outcomes that are not attributable to the risk factor for smokers. So again, lung cancer deaths that were, say, due to something else. So again, going back to that equation, how we calculated all that out, you can see where the factors come into it. So both the population who's exposed, that PE percentage, and also looking at the relative risk. And again, why we're using 1 in these circumstances here?
Relative risk is 1 in the control group.
Yeah, so those that are unexposed, the relative risk is always going to be 1 anyway, because they're your baseline. So again, just know this is how we calculate this out, and then I'm getting the percentage here. And the graph just so you can kind of reference back to that. Okay, so how do we use some of this risk assessment data? How do we actually put it to use once we have it? What can we do with it? So let's say if we want to estimate the benefit of an intervention on populations, right? So let's say that the population attributable risk data is often going to be used to estimate the benefit for a proposed intervention. So we can see that, okay, well, if we have this kind of effect, what kind of benefits can we expect to see from this? So for instance, the number of lung cancer deaths that would be prevented by instituting a smoking reduction program in a large population. Okay, so how many differences in the death can we see based on this intervention? So again, let's assume that in the U.S., the proportion of men who smoke has averaged about 25% or for more than 2 decades, as it did for much of the 90s. So we're going to go with our, and in this case, what would our PE be?
0.25.
Yeah, and it being 0.25, because again, 25% of the population of those men were smoking. So we're going to go with that constant there. And then assume that the amount of smoking has been constant among men who smoke, and that the lung cancer death rate in this group also would remain constant. So if you were to calculate this out, you would see that the rate per 100,000 in this case would be that the rate of lung cancer deaths in the total adult male population would be weighted average of the rates in smokers and non-smokers. So essentially what you could do when you calculate this out is that the rate of smokers times the weight of the smokers. So again, that 0.25, so you can do that 0.25 times 191. Plus the weight of the non-smokers, which would be 0.75. So again, that's just the PE, 1 minus the PE. In this case, it would be 0.75 times the rate of the non-smokers. So when you calculate that out, this ended up being a rate of 54.3 per 100,000. Okay. So again, this is going to be the rate of lung cancer deaths that were due to those that were smoking, in excess due to those people who were smoking versus ones that were not. So another way we could do this is that the PAR is also going to be expressed as a rate per 100,000 male population would be calculated, as you can see here. So you did at 54.3 minus 8.7. we ended up having a number of 45.6. So if a major smoking reduction program were to reduce the proportion of adult male smokers, say from 25 to 20%, just as an example, for an extended period, the lung cancer death rates for male smokers and non-smokers remain constant. So we're not getting any better treatment. We're not getting any worse treatment for lung cancer. It's still going to happen at the same rate. What would be the difference here? What kind of revised rate can we get if we were to have that reduction of PE from, say, 25 to 20? So if I were to do that, if I were to change my calculation here, end up getting a larger proportion of people who are not smoking versus those that are, that went down. And so you end up getting this number of 45.2. So we can take this and start to make some comparisons now between the 25% rate of smokers versus the 20% rate of smokers. So under these conditions, you end up seeing the PAR in this situation with the new number would be 36.5. So the difference between the first PAR of 45.6 and the second one is 36.5, or otherwise it would be 9.1 per 100,000 adult men. So essentially what that's saying is if you were to reduce the number of people smoking from, say, 25% or 20%, you would end up having 9.1 per 100,000 adult male not die from lung cancer. Okay. So a smoking reduction program would end up preventing about 9 lung cancer deaths per 100,000 people per year. Okay, so is that a good thing?
Depends how much money you're spending to get the 9.
Whoa, there's the frugal one in the group, huh? Just kidding. Yeah, so again, it's all going to depend on, if it costs, a gazillion dollars to do this, maybe it would not be super cost effective, right? So that's one of the things you're going to start considering. So if you were to extrapolate that out, because that's just per 100,000 people, let's say that for 100 million men, the intervention will be responsible for preventing about 9,100 deaths per year. So again, it's all going to be relative to what numbers or what rates you're looking at there. So if there were a similar number of women and they had a similar reduction in smoking rate and lung cancer death, you'd expect that to basically double for, because men are roughly 50% of the population. So, again, looking at this is just a way we're able to calculate all of these this information. So we already talked about each of these in detail, so you can kind of go back to this and kind of review for that. So when you have that kind of information, then you can start to do things like cost-effective analyses. So in this analysis, the investigators are estimating the cost in dollars of an intervention with the corresponding effects of that intervention. So how much does it cost per case of lung cancer averted does this intervention have? So the effects are commonly measured in terms of the number of injuries, illnesses, or deaths being prevented. And then it's going to be generally more difficult to measure effects, and it may take a long time to measure over a long period of time. So in the smoking reduction program, let's say, for instance, that the cost of the program was $1 billion per year. Reduce that from 25 to 20%. If 18,200 lung cancer deaths were prevented per year, remember how we calculate that out, basically it ended up causing a roughly $55,000 to prevent each death. Okay. If the cost of the program were assigned to the 200 million adults in the population, that's roughly about $5 per adult per year. Does that sound like it's cost effective? Maybe? Think so? Spent $5 in every single American, I can end up preventing 18,200 deaths per year? Possibly. Let's look at it. So in other ways, the way you could look at it, though, if you actually looked at the number of people who are quitting, that 5% reduction there, you'd end up seeing that it roughly would cost about $100 per quitter per year, right? Because even though you're maybe spending, say, $5 on every single person in the U.S., like a lot of them weren't smoking in the first place. A lot of them probably would not have started smoking, but you're reducing the people that did smoke to turn them into quitters, essentially. So for those people, that 5% would be roughly $100 per quitter per year. So, in addition to preventing lung cancer deaths, you'll also see that that something like a smoking reduction program would also offer other benefits. So you'd have a reduction in the rates of various non-fatal illnesses among smokers. You have the reduced number of MI, COPD, all kinds of other cancers as well. And so if the assumptions were accurate, and if all of the positive effects of smoking cessation could be included in the analysis, then the cost per health benefit would be much less than what was shown previously. Again, if you're putting that into relation to what it would cost to treat, lung cancer, to treat the COPD, to treat all these other things that could pop up here. And so the cost effectiveness of the program would end up varying and depending on how the outcomes of interest are really defined. So again, they usually have kind of standards for saying, okay, if we're treating someone with lung cancer for 10 years, this is what it would cost us, And so these are analyses that have been done across, like big third-party payers and things like that to come up with these kind of analyses. So to calculate the benefits of a smoking reduction program, the investigators would have to convert the positive effects, or that reduction in lung cancer deaths, into dollar amounts. And so the calculation of benefits would consider a variety of factors. So one would be a savings in the medical care, and also an increased productivity from the added years of life. So that's one thing that I never really considered when I was kind of going through learning this stuff, is you're also looking at someone who is maybe more productive for a longer period of time instead of being, say, debilitated with, say, lung cancer, right? So that can be a really big impact, especially if they you're affecting a large number of people who can be working for longer. So it requires an estimate the average cost of care for one case of lung cancer. So say like in a dollar amount in terms of productivity of adding 1 year of life. So what would it cost to end up doing that? And then the average number of productive years of life gained by preventing lung cancer. So how long could we potentially extend those people's lives on average if you prevent that lung cancer from occurring? So other ways to describe the values of interventions, the anticipated value of an intervention, whether it's, say, a vaccine or type of treatment or some sort of change in a behavior. You can talk about it in terms of absolute risk reduction, things like that. You can look at it in relative terms. And then you can also look at the reduction in the incidence density, or that reduction in risk per 100 person years. So you guys remember incidence density? Talked about that, like if you're measuring, say, 3 people for, say, 10 months each, and they end up having, say, 5 cases of acute otitis media, you'd have having 5 cases per 30 person months, right? So remember incidence density, it's an important one. So they can be expressed in lots of different ways, but the expressions may not give the patients or physicians really a good sense of how much impact a particular intervention may have. So there are easier methods to really communicate different things, because it's hard to say, like, hey, did you know that by stopping smoking you would actually end up saving yourself this much money and you'd have this many extra years of life? Do you think that would convince a lot of smokers to quit?
No.
Probably not. So, so because of that, you need kind of easier ways to be able to communicate this kind of information. So again, if we're looking at absolute risk reduction and the relative risk reduction, we already know how to calculate these out. Again, it's easy to understand, saying that, hey, if you went from, say, smoking, you have a 10% risk to, say, a 2% risk, 8% reduction in your risk. That's a little bit easier to understand for some people. Get another situation here. If you said assume the yearly risk of a certain disease is, say, 1% in the presence of the risk factor, and say 0.4% in the absence of the risk factor, you can calculate it out to say, hey, you have a relative risk or absolute risk reduction of 0.6 or 60% reduction in that risk of you developing that outcome based on your risk factor, right? So it's relatively easy to express to people. An intervention that removed the risk factor would be reduce the risk of disease, say, by 0.006 in absolute terms. And so in this case, again, like I mentioned, we had a 60% reduction in that risk of relative terms. So when that risk of relative terms is applied to the effectiveness of vaccines, you can oftentimes see this being expressed as either vaccine effectiveness or the protective efficacy of a vaccine. So that's where you might see those being expressed as well. So again, your risk of, say, the reduction in risk of getting measles after getting the vaccine versus not having it. All right, so picking up, we were talking a lot about risk, not the board game. If you wanted to play that, but now we're going to move into a related topic, which is going to be our number needed to treat or harm. We've kind of alluded to this previously when we were looking at our biostat section of the class. And so we know that the measure used to describe that practical value for a treatment is called the number needed to treat. Do you guys remember how we calculate this?
The reciprocal of the ARR.
Which is what? What's the ARR?
Absolute risk reduction.
Yeah, right. So it's the absolute risk reduction. So you're looking at a absolute risk reduction. You're taking the reciprocal of that, or 1 divided by your risk reduction, and that's going to give you your number needed to treat. Similarly, if you were to have an increase in risk of something occurring, a bad event, you can do the reciprocal of that, and you get what? So the number needed to harm. That's what that value would end up being. So I'll show you that on the next slide. So, for example, if you had you were looking at a study looking at a course of hyperbaric oxygen therapy used for healing leg ulcers, let's say in 1/3 of patients, they end up having a good effect. They end up having healing of their ulcers. And so in this case, if you were to look at that, say they developed an absolute risk reduction of, say, 0.333, and you were to take the reciprocal of that, the number needed to treat would be 3. And so what does that mean to you? That would mean that I would give hyperbaric oxygen therapy to 3 people. How many people would benefit from that? One, right? I would expect at least one to benefit from that. So obviously a larger number is going to be good or bad. Generally worse, yeah. So you generally want to have a smaller number needed to treat. So if I were to give, say, if I had a number needed to treat of 2, I would only have to treat 2 patients with hyperbaric oxygen to get some additional benefit there. So smaller numbers are going to be better here. Obviously, for number needed to harm, you want larger numbers because you don't want to harm your patients necessarily. So this is good for helping to make comparisons between different treatments, especially if you can look at the cost of therapy between things. So if I had something that had, say, a very large number needed to treat that was very inexpensive, you can compare that to something like hyperbaric oxygen, which may be much more expensive but would maybe be more effective. And so you can kind of start making some better comparisons there. Does anyone know what kind of poisonings you can treat with hyperbaric oxygen? Yeah, carbon monoxide, absolutely. Yeah, it helps to clear the carboxyhemoglobin a little bit faster. So similarly, the idea behind number needed to harm is going to be the same basic principle for number needed to treat. It would just be looking at your absolute risk increase. Right? So if you did that, the incidence of, say, erectile dysfunction with patients with antihypertensives, you would see risk increase in those male patients, and then you would just take the reciprocal of that and get your number needed to harm. So say, for instance, we were looking at one clinical trial that can illustrate this concept. So say we're looking at the rates of colic that were occurring in infants who were either fed iron-fortified formula or those that just had regular formula. And so in this case, the mothers of all the infants who were asked to report whether or not the infants had the symptoms of colic. So that was kind of their outcome here. And so when they looked at the occurrence of colic, they saw that in the ones that got the iron-fortified formula, they had 56.8%. And then in those that just had the regular formula, it was like 40.8%. So to get the absolute risk reduction or the risk increase, how would you calculate that? Just do the risk of one minus the risk of other, right? So in this case, you do the iron fortified formula. That risk there was 0.568, right? So 56.8 minus that 0.408, you end up getting that 0.16. So we had an absolute risk increase of colic of 16%, right? So if you were to take the reciprocal of that, you end up getting 6.25. So again, what does that end up meaning?
You'd have to feed 6 kids for 1 kid to have colic.
Yeah, so if I've had 6 kids, or between 6 and 7 kids, this iron fortified formula, if I would end up having 1 additional case of colic, right? You still end up having some baseline kids who would be developing colic anyway, just because of the fact that we know even if you got regular formula, some kids are just going to develop that anyway. So that would be in addition to the 2 or 3 that may have developed it just by normal course of treatment, right? So very similar concept. Again, anytime you're having a risk reduction or risk increase, the difference there, right? You don't want to do like a risk ratio and get the reciprocal of that. That doesn't really give you any information there. But a absolute risk difference, by taking the reciprocal of that, you'll get your number. So even though they're helpful for describing the effects of treatment, several points should be emphasized. So first off, one author noted that a complete analysis of number needed to treat and number needed to harm really should provide confidence intervals, right? So ideally, if you're doing statistical tests here, you want to develop confidence intervals, because what could that potentially tell you?
Significance.
So yeah, so one it would tell you significance. What's the other kind of thing it would show you? What kind of gives you the range of potential harm or good you could be doing in that case, right? So we always said that we'd like to have more narrow confidence intervals if possible, so you have a much more sure idea of what the true value is going to be. But if it's very wide, and for instance, if say your number needed to treat went anywhere between say 0 to 100, like that doesn't really give you a whole lot of confidence there that you're going to get any. You're not really sure what benefit you're going to get from that. So confidence intervals are important for describing these. Another thing, it's important to look at the length of time that the treatment is needed to obtain the full benefit. And this is also important when you're looking at costs associated with these interventions, to see what kind of benefit you'll get over what type of period of time. We're talking about 1 year, 6 months, 10 years, whatever it happens to be, that should also be incorporated into your analyses. And then the net benefit from the intervention should be reduced in some way to account for any harm that are being done, right? So anytime you're giving treatment for something, say for hypertension, you may get benefits of, say, longer life, but you may have other side effects that should be factored in to that as well. And it becomes a lot more complicated, if you're looking for maximum precision, because you have to start calculating things like, the proportion of treated patients who would only have benefit from the intervention, those that would only derive harm, right? Because we know that some people will be non-responders and may have adverse effects, and then those who will get both, right? Because we know some people can tolerate some degree of adverse effects, but as long as they're getting some additional benefit from that. So it gets a little bit more complicated than just a simple number needed to treat or harm, but that's kind of the basics of it. So how can we apply these kind of risk measures to counseling of patients? Using measures of risk, a provider can make the following estimates of impact of smoking. So kind of going back to our smoking example, looking at this, we said smokers are about 22 times as likely as non-smokers to die of lung cancer, right? Going back to that 1986 information we were looking at. And so they were also estimating that about 95 out of every 100 lung cancer deaths in people who smoke can be attributed to the fact that they smoke. So a large percent of that risk being related back to those that were smoking, right? That was the risk factor that seemed most associated with that. And so say there's about 158,000 deaths from those respiratory tract cancers in the US, 88% which would be attributed to smoking. So in this case, we know that 89% of 158,000 would be at 139,000 of those deaths per year. And so assuming that your risk of fatal lung cancer among the smokers is say 191 per 100,000 per year, that basically equals out to be 0.00191 per year. So using that number, because that number by itself would not be super useful for talking to your patients. If you were to take the reciprocal of that, because saying that it would be your risk, what you could say is, or in this case the harm, is that by dividing that 0.00191, again the reciprocal of that basically comes out to be about 524. So essentially what you could say is that you'd expect 1 of every 525 adult smokers to die of lung cancer each year. So kind of get relating that back to your patients, saying like, okay, this is what's, if you have this many people smoking, this is the additional people that are going to die because of that. Can be a little bit more kind of concrete example of how to relate this information. Okay, so we talked a lot about risk, we talked about rates, odds. It's important to remember, what type of data you're looking at, what kind of calculations you can do. If you're looking at absolute and relative measures of risk, can you do that with prospective data? Right, so we're looking for risk differences and say risk ratios. Can I do that with prospective data? Yes, absolutely, right. So that's what we were talking about mainly. That's why the prospective data is a lot more robust in that sense. But when you're looking at more retrospective data, like those case control studies, can I do absolute risk differences? Can't do absolute, right? You can do things like odds ratios and whatnot, but the problem when you're doing those retrospective studies is you oftentimes don't have the whole population that could be at risk because you're matching cases with controls. And so remember the differences there and when which kind of risk might be appropriate to apply to those. And so obviously the greater the ratio, the greater the difference, the exposure, whatever we're investigating is going to be making on these patients. So the impact of risk factors on the total disease burden can be measured in terms of the attributable risk percent. You can do that for an exposed group, or we talked about how you can apply that back to the population. So remember how the differences there were done with that PE variable when you're applying it back to the population. And if it's known how much a preventative program can reduce the risk ratio and in whom, the total benefit of the program can then be calculated. So looking at the cost, there's a lot more data or information that goes into that, but you can start to get an idea of how these interventions might be useful for your population. So any questions on risk or any of that section? Yes?
I don't know if I just didn't understand this well, but on slide 27 it says if the risk of the disease is relatively large, the odds ratio is not a good estimate of the risk ratio.
Mm-hmm.
So in regards to that, if say you do have a really high, there is a high risk,
Mm-hmm.
your odds ratio wouldn't be beneficial. So in like case control studies where you're looking retrospectively, how does that help? Like if there is a difference.
So if you look at how that's calculated, that would make sense. So if you're saying that a likely or a risk ratio is going to be the risk of the people that were exposed to whatever risk you're looking at, right? So if it was cigarette smoking divided by the total number of people in that population, right? So if you're looking at cigarette smoking, the number of people that died over the total population, right? So when you're doing the odds, if you're looking at that retrospectively, what you would end up doing is looking at the number of people who were smoking divided by, or the people that had smoking as a risk factor, the people that died divided by those that didn't, right? So the denominator is a little bit different there because you're not looking at the whole sample at that point. So when you have a low incidence or a low prevalence of the outcome in those situations retrospectively, you see that the odds ratio would be very similar because your denominator is going to be very similar as you would see with the risk. So if you have a low prevalence and your odds ratios, it's going to be very similar to your risk ratio if you had done that study prospectively. Basically, if you see a very high incidence or high prevalence doing a retrospective study, you don't have as good of an estimate of what that risk ratio would be, and so you can't necessarily say that, had I done a prospective study, I would have found these very similar results, right? Which is why it's tough to, especially when you're looking at stuff like tox literature or PEDS literature, you can't do a lot of those randomized controlled trials with prospective data. So we rely a lot on those retrospective data to say like, okay, well, we can't do this ethically, we can't do this prospective study, but based on the low incidence of these outcomes, we can say that this odds ratio should be pretty close to what it would be if we had done a prospective study. So it's kind of where they're getting at. And again, you always have to take everything with a grain of salt and kind of look at the context for it to see how much you can take from that. Yep. Any other questions? Okay.